o'clock, we'll get started. Welcome back. This is my last lecture. Very sad. So hopefully make it a good one. Don't know how you guys want to run it. If I run out of material, you can either hear my life story or you can ask homework questions, whatever you want. I don't know which one I'd go for. Just eat Frodo frogs down the front. So everyone who's on Zoom, you missed out. There's chocolate. Cool. All right. So where are we up to? Yeah, so you get Andy tomorrow. Andy's a really good guy. You've met him in the first lecture. I've worked with him for years. I don't work with him currently, but you'll learn a lot from him. He's actually contributed to Base Julia. So he's actually like made bits of the real language. So I am just an open source vampire. I just take stuff. I don't give anything back. Andy's the real deal. He actually contributes. So good to know people like that. Cool. Yeah, so we're on Unit 3, Final 1. So we're on to the Numerics one. We quickly did some stuff about CSV and JSON. It's not super exciting, but good to know stuff. Good to know that stuff. Did a little bit about plotting, and the important bit was getting into, we did a little bit about floating points. So this is, I've said about floating point several times already. In the first lecture, I introduced stuff about how the square root algorithm works and based on floating point. And I guess if there's anything I want to convey from this part of the course, like it's good to know how floating point's represented. Remember that it's this kind of strange thing that you're going to get evenly spaced between powers of 2. That's kind of a weird choice, but people smarter than me worked this out a long time ago. It's a standard pretty much. So all the different bit representations, the 64, 32, 16-bit. Yeah, interestingly enough, I said, we talked about floating point epsilon, which is like the smallest, where was this guy? See if I can get it. So float 16 epsilon, and this is in Julia. Is that big enough? A little bit bigger. Eps, float 16. This is like not much relative error before it starts to become a problem. Every time you're working with 16-bit floats, you're going to get this much fluff. It's actually sort of coming back to, I said, you'd be pretty brave to use float 16s. In neural networks, if you get like they call it a tensor processing unit from Google, like you can rent a supercomputer on the cloud. Most of those calculations are done in floating point, in 16-bit floating point, because for neural networks, precision is not the biggest deal. Believe it or not, because everything's kind of statistical and smudgy. It doesn't really matter. So yeah, that's the thing. And another important thing to know is that it's kind of random. The kind of errors you get from floating point is you're always going to get this little bit of fluff, and the fluff is not random. It's got a bit more structure than random. So like being careful about how you're going to talk about these things. It's got a bit of structure there, but it behaves almost like a random number between this eps, the relative error. So every time you do a calculation, you can kind of expect there's going to be this bit of fluff. And when you were doing float 64s, 2 to the minus 16, you're always going to get a little bit of rounding, not rounding, but a little bit of imprecision introduced by your operations. Has anyone seen, like, when they've done a comparison, like equals, they see something like 10 to the minus 16 when they've been doing anything for homework? Does that come up? Yeah, that's it, pretty much always. But the thing to remember is that it propagates. So this is just like for every time you do a calculation, how you compose these calculations will cause it to get bigger and bigger. So this approximate nature of floating point causes some strange stuff to happen. I'll just reiterate these two. You lose associativity, which is like my favorite. Like, depends where you put the brackets. They do not equal each other, but they almost equal each other. So it's not like the end of the world that this is happening. It's just that everything becomes a little bit more probabilistic or statistical. So there you go. That's that 10 to the minus 16 popping up again when you compare these differences. You have this small little bit of fluff that comes through. Cool. And this other one, that if you add a very, very small number to a very, very big number, the big guy eats the little guy and they just disappear. So this is the way that floating point addition is implemented in this finite amount of precision. You're just going to lose this stuff, which is our nice, neat segue into the next bit, where I showed my favorite one, my every 6-month problem. I have that guy. This is leading directly into numerical derivatives. So I think I said about this in the first, not first lecture, maybe the second lecture. I talked about trapezoidal integration, and you can use this mathematical definition of a Riemann sum, if that's not in the forefront of your mind. Let's go over here. I've probably got this picture. So, you know, when they were trying to work out calculus back in the 17th century, you know, you got a continuous curve, you're going to chop it up into chunks, add up the chunks. That's pretty much the definition of integral, as you let the limit as the little chunks go to 0. That's you know, use the mathematical definition to derive an algorithm for doing integration. Numerical derivatives, basically the same deal. We can, you know, been a long time since I've done this stuff, and you can all shout it at me. It's like the difference between saying, you know, f dashed of x approximately equals f of x plus h minus f of x divided by h. If you're going to say, you know, what's the definition of a derivative, the only thing missing there is the limit as h goes to 0. So, you know, back when we were talking about minimization earlier, you know, you basically just, you know, if you wanted to know the slope at a point, you can sample it here, fit a straight line. That's basically the definition of a derivative. Yeah, so this, though, is basically, you know, if we looked at this guy, big guy eating the little guy, floating point actually is very fun in this case. So what we can see here is that, you know, if we're just concerned about the mathematical definition, we were just concerned with real numbers, as it goes to 0, we would expect the approximation to become perfect as h got really, really small. We don't see that because floating point sucks. What we actually see is something like this plot down here. So I guess we'll just go through this line by line. Why not? It's simple enough. So what we've got here is a little inline function definition of the forward difference. So this guy's, you know, you can define the derivative to be forward difference, which means you step forward. Central difference is you take points either side. You can imagine doing a million different things depending on what you're going to do with it. This forward difference, though, is pretty straightforward. It's just f of x plus h. So we can take, we've got this nice diff forward thing here for a scalar function. So it's going to take a function as the first argument, the variable as the second argument, and h, which is going to default to square root of epsilon. So forward diff. So let's just say just to start with, to warm up, something I can handle the derivative for, being old and out of practice. I can work out what the derivative of that is. f of x. Okay. So if we're going to run this guy, diff forward f1 with no argument, what's the derivative of f going to be at, f of x going to be at 1? Anyone? Hey, we can all do it. Okay. Just to check. Okay. So we notice, though, if we did that, you know, we've got a little bit of difference there. So natural thing to try is we said, you know, we started with h equals square root eps as a first guess. Oh. Let's make that guy a little bit smaller. So, oh, I put too many brackets in there. Oh, sorry, square root eps. I put a 2 in there. What am I doing? H. Okay, so we'll compare that to the last one. Okay, so, you know, error is going to change depending on what we do. If we make it even smaller, divided by 10, see if we can get a bigger effect. Doesn't actually get better as we go smaller. Like if we're out in the extreme in the other direction, so let's say we take a step size of 1. Oh, that's massively wrong. Then we go 0.1. Smaller. 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 Blah, 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 blah. So basically what we're doing in this plot here is we've taken a slightly more complicated function, sine squared x. We take the derivative analytically, 2x cos x squared. Hopefully you guys can all do that better than me. My brain's ossified. I'm out of practice with calculus. I get like the horrors if I have to actually do a derivative. What we're going to do here is we're going to evaluate it at 2 different points. And we're going to step through a range of h to different powers. So we're going to make it like really, really small, h. So this is a way of defining a range. It's probably worth seeing. What we're going to do is we're going to take different powers from -14 in steps of 0.01 to -2. So that's going really, really small to reasonably big. And we're just going to do that thing I was doing, but instead of doing an absolute error, we're doing an absolute relative error. That's a little bit confusing, but we'll take the absolute value of the relative error. So divide it by the value. That's all that's going on here. And we plot this as a function of thing. And so this is, again, I've probably said this a couple of times, but you know, mathematics students, mathematics is kind of pure and beautiful. All the abstractions work. When you're with computers, everything gets a little bit dirty and the details of the implementation leak. So because we're using floating point in this case, this thing that the limit as h goes to 0, our errors are going to get better and better and better, does not happen anymore. They start getting worse again. And really annoyingly, it's not obvious. It depends on the function and the value of the function as to where this approximation is going to get terrible. It's not like you just go, oh, if you pick h equals blah, it'll always work. It depends on the function and the value of the function. So that's a nightmare. But these are the kind of things you're going to encounter. So I hope that's kind of clear. It's very worth, just probably because it's in your homework, is like this extends to multivariate functions in a pretty natural way. So if you think about the definition of, got to remember second year, you can talk about, here we said the definition of a derivative is something like this. The limit as x goes to 0. If I have a multivariate function, I've got to take the partial derivative. So what's the difference between this derivative and partial derivative? What am I going to be basically doing in this case? What will I take a step in if I'm going to do the finite difference on a finite difference approximation to the partial derivative of a multivariate function? Yes, exactly right. So for that one, you've got to say which variable you're actually stepping in. And if you're going to do it, you have to do them one at a time, right? So like if I've got an x, a y, and a z, I think we can handle doing this. 2 times x. More stuff I can handle actually taking the analytic derivative of. That's what I'm choosing these for. 4 times x. 4 times 4. So if I go f of 0, 0, 0, get a function like this. I go 1. What's that? Oh, good catch. I'm glad you guys are here. Thank you. I was wondering why that didn't work. Good job, good job. Okay, so if we're going to do finite difference approximation, we basically have to take a step in each dimension. So didn't set this up very well, but then divided by your dx. So that's like the derivative with respect to that first coordinate. Oh, not happy with me for some reason. Anyway, probably because I've got to go dot minus. Oh, I did tuples. Anyway, bad example. Anyway, so if you're going to step in each one, probably just redefine in terms of an array. That would probably be the way to fix it. There we go. Hey, we can do it now. So yeah, that should be, if we look at what we defined x, that should be something like 2 times x, 2 times e to the 2x as that first one. So times x, 2 times x. Oh, just that. So that first derivative, because we've taken a big step, it's going to approximately take that. So again, this is an interesting one to think about how things scale. So if I have a multivariate function and I'm going to do finite differences, so it's a multivariate function that returns a single variable. how many steps do I have to do for each one? How does it scale with this, how many inputs I have? So just to be super clear, that'd be the first one. If I want to do the second one, I got to go, okay, now I want to get this next derivative. And if I do the next one, I want to go, so it's, no one wants to guess? Hey, that's right. So it's linear, and this doesn't seem that bad, but if you've got a very expensive function to evaluate, that can be a killer. The difference between, doing, if you had if you work out the analytic derivative, it's going to be way faster. But if you have to do finite differences, you have these kinds of errors to fight, where it's actually the error I get depends in a kind of annoying way sensitively on the step size, and it's linear in this number of variables. So let's say you're doing optimization of something important, like, so some business problem, and you have 1 million variables. That happens all the time, or 1,000 variables even, but the function takes an hour to evaluate. It's sometimes not practical to do this finite difference method to evaluate functions. So an example of that would be if I'm a physicist or an engineer, and I have like a fluid dynamics simulation, and it takes like a day to run one iteration of my model and trying to work out like how to make a car more fuel efficient. Or I'm going to put it in a CFD simulation, computational fluid dynamics simulation, set the numbers for the shape, and I want to go like, how big should I set the roof of the car to make the drag really small? Okay, we'll set one variable one day, and I go, cool, I want the sensitivity of the shape of the roof to the drag. I'll bump it here, bump it here, bump it here, bump it here. Each one of those is a day. Kind of get the idea that that's a killer, right? And this comes up in neural networks, because what you're trying to do when you're trying to fit in machine learning is the same thing. You've got this expensive function with lots of variables. You're trying to go like, got this super rubbery function with lots of magic numbers, and I want to optimize all the magic numbers by gradient descent. That becomes a really big problem. So the magic solution that I wished I'd known is this thing. It's going to change your life if you have to actually do, this is why I can't do derivatives anymore, is this thing called automatic differentiation. So you can go off and learn about this. So has anyone heard of these libraries like TensorFlow or JAX or things like that? If you ever go into data science, this will become part of your life. They're basically libraries for doing automatic differentiation, which is you can use a special type of number to pass into your function, and you can use basically Taylor's, what is it? You can use like a Taylor series, or sorry, no, it's a chain rule, I want to say. These things called dual numbers. So much like passing a single number in, you can pass two numbers in, and basically the squared terms cancel. So you can get this special algebra with dual numbers that lets you get the derivative basically for free. So these are very, very cool. So this depends, like this is actually like where if Julia gets as good as it could with doing automatic differentiation, it will be transformative, because basically if you can write a function, you get the derivative for free. In my professional career, I have literally spent, I don't want to overstate it, but I don't want to understate it. It was 2 months working out the analytic derivative for a function and validating that it was correct, because it was for an important problem. So, if you can write the function out, you get the derivative free if you can overload with this special type of number. So the magic library, you probably wouldn't interact with this one so much, but there's a library called Flux, and there's a library that uses this thing called Zygote underneath. And if you can derive, I'll choose a more interesting function, but I think I did this here. So I've got 3x squared. So I've got an anonymous function that takes x and y. 3x squared plus 4y plus 1, and I'm going to evaluate it at x equals 2 and x equals 0. So Julia startup time, because I didn't pre-compile this one. It's a big deal, but you basically get the derivative at any point. That one's not going to change. I don't know how good you guys are at doing this stuff in your head, but what you will get is 2 floating point error, it's an analytic version of the derivative without having to do all the analysis, just by using a special type for the number. And the basic idea is using the chain rule to, just check I'm not mute. Yeah, just using the chain rule and some special types to get it through. So that's pretty magical and very, very useful. So if this comes up, good for you. So you won't get a nice expression for the derivative, but you get the derivative itself. So depending on what you're trying to do, for me, it's nearly always optimization. And you're always trying to do optimization because you've got a function at a value and you're trying to find the argmin where this cost function minimizes. That gives you a gradient direction to search in. Any questions on that? Yeah.
How does it actually differentiate?
So it's instead of passing a float, it will pass a dual number through. And every time there's a product, because it's like epsilon times epsilon, if you're thinking about this definition of a derivative, it cancels those terms out. So there's a special algebra for these dual numbers that it works through. There's different ways it can actually calculate this. It's kind of well beyond the scope of this course, but that's kind of like the hand wavy version of it. What's that? It's basically like just two numbers, like two floating point numbers that get passed through. And so it's when... Yeah. Yep. Yeah. Yeah, that's right. So all you have to do is set up your function as if you're going to pass through a real number, but instead you can pass through a dual number. It will do some clever calculations on the back to work out when any of these product things happen and cancel them out and then give you the answer. There's different ways of doing it. There's reverse mode and forward mode if you want to go off and read about it. It's like a big, big thing. I'm not an expert, but I actually use it a lot myself for optimization, the result, because if the abstraction's good, I don't care. I just want the result, right? As long as it works, it's great. Yeah, so like there's a whole big thing of like TensorFlow is this big thing, like big software project in Python that people use to set up neural networks. If you're going to go and work in neural networks, they all use TensorFlow pretty much. It's just automatic differentiation under the hood. Cool. And yeah, keep that in mind. That's if you're doing finite differences, multivariate, you've got to step in each one, and that can be a killer. Cool. All right. Again, we talked about this. This is a chance for me to go off course a bit, which I'm excited about. Okay. So I think when I talked about this in the lecture, all your intuition was fantastic. So I don't really need to say too much. So basically, integration's super important. Hopefully you realize that. Integration to actually do is hard. Like derivatives are, I get the terrors, like I said, if I have to actually do a derivative now, being post 40 and out of practice. But integrals are even worse. And you probably noticed this, right? You learn all these nice methods for doing derivatives analytically, but nobody teaches you nice methods for integration, right? Like you might get integration by parts, and sometimes that really sucks to do. It's really hard. And it's not obvious that integration is just hard, right? Like it is just anti-differentiation in a sense, but to actually do analytically is very hard. Nicely though, it's really easy to do numerically and very accurate. So you can get hyper-accurate things for numerical integration. Now, I guess for me, my evolution of my career is like as a pseudo-statistician, nearly always it's like trying to normalize a probability distribution is why I'm doing integrals. Like if I'm actually trying to turn something into a probability, I need to work out what's on the bottom line over that integral over all the states or whatever it is. And if you're trying to normalize, so it tends to be high dimensional integration. So I'm going to do a little demo of that. I think that we can use that time that way. Okay, so Riemann sum is so yeah, I guess this stuff's all just staring at this thing and going like, okay, we can decide to evaluate the function on the grid. That's one way you could define an integral. And that's got a special name. It's just trapezoidal rule. What you could do instead is like, oh, well, there's nothing special so much about the endpoints of the grid. Maybe I could do it on grid. So like this point here, you just drag that down so it's there. That's a tiny bit of accuracy improvement, not so much. The big win is if you do something where you're going to make an assumption about the smoothness of the function and fit a polynomial through it. So an interpolating polynomial through those evaluation points, that's the one that gives you the big win. And I guess there's a whole zoo of these guys. They're called the Newton-Coates formulas. Has anyone come across this before? You've done this in another class? Kind of thing I'd had to learn to death. But maybe not so much. Basically, they're just like, okay, hopefully if we go to Wikipedia, it's got the whole zoo of these things. Yeah. So you'd use a Lagrange interpolating polynomial to go to higher and higher points. It's more smooth. You're going to get a better and better job. Some stuff about high degree, but basically what this turns into is all these different rules for integration as you go to higher and higher things. And most people, like Simpson's rule is kind of like, you look at truncation error, you don't really win by going super, super high order. They kind of just work, so it's fine. So I don't want to say too much about that because it's kind of obvious. It's really just like, fit a polynomial, work out, because you've got a polynomial, you can work out what the analytic integral for that is. It's easier than doing this thing. If it's smooth enough, that should be better. Okay, here's okay, I got an educational point that's kind of thing though. It's like, as soon as we're getting into this stuff, you really quickly get to the point where there is no best thing. It really depends on your particular problem. And the more you know about your problem, the better you can do. So there's a saying in software that worse is better. You've probably heard that before, maybe not. It's like, why is Windows the best thing? Like, why does everyone use Windows? It's not better than the other things that are out there, and you have to actually pay for it too. But you get the market share, you get everyone, you get the ecosystem. That's the thing that ends up winning. This is kind of another example of worse is better, where for particular problems, a dumb thing can work really, really well, as long as you know something about your problem. And I've tried to give a demonstration of this here. So we've got these two integration formulas where we've gone, okay, we'll just do trapezoid rule versus Simpson's rule. Oh, I did midpoint rule even, sorry. I did midpoint rule. Okay. So not even clever at all. So I've gone for this higher order method for Simpson's rule. So it takes a function, takes in an A and a B, and it takes in a method, which I've given as a string. If the method equals midpoint, we're going to do this. If the method equals Simpsons, we're going to do this. Else we're going to error out and say, I don't know what you're talking about. We have to add that method if you want to do that. And I've got two functions here, and they're a bit specially chosen. So the first one is a cos wrapped inside an exponential and just an exponential itself. Now, again, I get the horrors when I do have to do a derivative analytically. It's even worse if I have to do a numerical integral, an integral analytically. But this is one of these things that called a Bessel function is what you get for this first one. If you try and do that integral, I did sit through this and work this out. I remember doing it. And the other one's just, we're doing a definite integral between A and B. So we're going to get 2 pi times some funny Bessel function that depends on the coefficient at the front. And for the other one, we got x 2 pi minus 1. Now, what we've done here is similar to doing the numerical finite difference approximation. We're going to go, cool, let's accumulate some of this stuff and see what the errors look like. So kind of said that there's lots of ways to skin a cat. When we're doing this integral for real, I've just defined it in terms of, I've just defined it in terms of A and B, but if you want to do more than that, you just have to keep applying it down the chain. So what I've done here is I'm applying a map. So the sum of the map of this Riemann sum over dx. And I'm going to do the same thing for this Riemann sum dx Simpsons. I'm going to push that into this array, and we're going to change x of s. So basically, I'm doing same sort of deal where I'm going to go, like, cool, do different step sizes, calculate these two integrals, compare them to the numerical integrals, and plot them on a plot. So kind of annoyingly, F2 is the simple one, right? So this is x. So this does what you would expect to see. So if I evaluate the midpoint rule and I plot the errors, as I do more and more points, so basically if I shrink dx, I'm going to put more and more points in my integral. The error between this goes down. Log of the absolute error reduces. And if I compare it to Simpson's rule, which is this higher order method, this is this one where you bothered to do this Lagrange interpolating polynomial, higher order method, should get better asymptotics for the error. So yeah, you do, it flogs it, right? So log absolute error for this one is much, much better. That's good. However, if we look at the next plot, they're almost identical. So this is kind of strange, right? So this is actually a property of the function itself. So this guy, if you have smooth periodic functions, midpoint rule works really, really, really well. Like, you don't need to do these higher order methods. If it's periodic and smooth enough, don't even bother. So this was something like I came to this backwards. So assume everyone's familiar with an encoding for images called JPEG. Anyone have any idea how JPEG works? It's basically working on Fourier transforms, or a restricted type of Fourier transform called the discrete cosine transform. So it will do Fourier transforms on little patches in the image. And then in that basis, it's going to be more sparse than in the original basis. So you can get rid of some stuff and you don't lose too much information. I will talk about this a bit more just after this. So I'll talk about image compression. So yeah, so this encoding is like a magical algorithm called JPEG. It's a lossy compression algorithm. So if I say lossy versus lossless, the difference is if I compress this thing in a lossless way, I recover the original thing exactly. If I have a lossy compression algorithm, it's approximately true when I reconstruct it. So there are two classes of compression algorithm, and JPEG is perceptually basically lossless. For people, we can't tell the difference. But if you compare it by going like, I'm going to look at the L2 norm between these two images I've reconstructed, they're going to be quite different. But perceptually, we see them as almost the same thing. So this is exploited in when they do a Fourier transform. When they're doing a fast Fourier transform, it's called, they just use the midpoint rule. And I always wondered, why did they use the midpoint rule when it's kind of worse? You could use one of these higher order methods and it's better. If the thing is smooth enough and periodic enough, you don't need to. That's why. Cool. So, any questions on that? That's the basics of numerical integration, really quick. Okay, next thing to worry about is higher order integration. Okay, higher order integration, as you go up in dimensions, things get awful really quickly. I'm going to talk about that in this one. So this is actually the part of my job, though, is I'm working in machine learning. I'm trying to turn things into probability distributions. So I think, did I have a thing up here on that? Maybe not. It's basically that part of Bayes' theorem. So like if I've got basically what most of my job is actually is like, I've got some data. What is it? And you're going to go like, what's the probability of this thing being blah given this data? And Bayes' theorem turns that around and goes, well, what's the probability of getting that data if it was blah times the probability of blah divided by all the different ways you could get that data. And because of all the different ways you can get that data, that ends up often being a very, very high dimensional integral, like hundreds, thousands, millions of dimensions, really quickly happens. So this is a very practical thing of like, how do we do integration in really high dimensions? So this is kind of interesting, and I was going to do, so there's these fancy methods, this idea you'd have of like, okay, cool, we'll just cut it up and do fancy polynomials and fit them, fit shapes in between the grid points. That works, but it tends to die at a very surprisingly low dimension. This all falls over. So we've got an example here. There's these things called, this is like state-of-the-art stuff, this H-cubature. I guess we can just run it. So we've got some funky functions, not too complicated. You can imagine doing the analytic derivative of that. So it's f of x equals pi length of x. So x is a vector in this case, like it's not necessarily going to be a scalar, it could be a vector. And we've got this like inner producty thing of x dash times x. So what we're going to do is we're just going to step through. Let's just run it and see what happens. Hopefully it's not too slow. So dimension 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that, for dimension 1, it's basically, so the H-cubature method, go look up that method. It's basically the same idea where you're going to go fit surfaces if it's 2D, rather than a polynomial, you're going to interpolating surface in n dimensions. And, 1 dimension good, 2 dimensions okay, 3, 4, 5, it's going bad, going very bad, very, very bad. It hasn't even hit 10 dimensions yet. So actually kind of weird. So has anyone got any ideas of like, who's really good at this stuff and go like, hey, this is what you should do? Or has anyone learnt it somewhere else? And anyone think of a strategy that you might do for doing integration in high dimensions? Okay, this is another case of worse is better. What's the dumb thing you could do? I'll tell you a dumb thing you could do. I didn't come up with this dumb thing. Some really smart people came up with the dumb thing. So maybe it's not that dumb. If I have something like, imagine that's sorry, I'll delete it. Let's say I want to take the integral of something like an ellipse, okay? So like, you know, that gets complicated pretty quickly. What I can do is say I have access to some source of randomness. Let's try and, this is hard. I always try to draw these things beforehand because you got to make it look right. So I can draw random numbers. Say I can draw random numbers in a unit square, right? Here's a really dumb way to do integration. What I can do is I can draw a random point and I can go blah, L2. Why is it doing that? That's not what I wanted. So I draw a point. It's inside the circle. And I've got a test for inside, outside the circle. Let's say we've got that condition, right? Inside the circle, count inside 1. Outside the circle, on the second draw, that's outside. So I'm just going to randomly throw points at this thing and just go inside, outside, inside, outside, inside, outside. And because I know the area of the box, because I can do that integral, right? That's easy enough. I can just count how many times it ended up inside the shape and outside the shape and look at the ratio. And the ratio of that to the other integral is an approximation of the integral. State-of-the-art method, this is. They give it a fancy name, Monte Carlo method. So, can you guys see this screen? Do I need to make that bigger? Probably need to make it a little bigger. Okay. So I've just done a demonstration of this. If you want to go and find this code, it's not in your notes, but it'll be in Paul's silly test repo. If you go and stalk me on GitHub, you can find this. So what I'm going to do is exactly what I just said, where I'm going to look at an M ball in high dimensions. And I'm going to do this Monte Carlo sampling where I'm going to go inside the ball, outside the ball, and increase the number of dimensions. Cool. So I've got a function here that's some other person told me is the answer because I can't do that integral, but I'm sure one of you guys could. Of just going, it's to do with this gamma function we came up with. Who remembers that from the first section? Gamma function, what was that? Sorry? Yep, that's right, that guy. So it relates to this gamma function. There's something to do with the radius, number of dimensions, radius to the power of number of dimensions. So this is, if I have an n ball and I'm going to look at the volume of this thing, that's an expression for it. And trust me that that's true. I can do this code though, where what I'm going to do is I'm just going to randomly choose a number of samples. I'm going to choose an R and a number of dimensions, and I'm just going to go, right, throw points at it, sample it, look at the ratio of inside to outside. Hopefully you can see that code. I've put in a random seed so I can debug this thing for I equals 1 to num samples. This is my test of whether it's inside or outside. I just check whether the norm of this thing is smaller than the radius or not. Hope that's clear. Is that clear? So that's really simple. Inside the ball gets a +1. The ratio is just the number inside the ball to number of samples, and the volume of this cube is going to be this thing. So that will be a Monte Carlo estimate for the volume. Cool. This is the equivalent thing. This is more yuck, right? Like, so I'm doing this cubature method, this H cubature method for like half of the sphere, and then I'll add the other half, whatever. I've made a function inside a function. I think someone asked me about whether this was okay to do. Was anyone here? Is that anyone here? Yeah, I did it. It's fine. If I did it, it's fine. Anyway, you're always allowed to do it. Yeah, so I did this cubature for a sphere volume. This is the same thing as the other thing in the notes. So let's have a look at this guy. Okay. That's the equivalent thing for the sphere volume. I'm not going to talk about that too much. So we're going to fix the radius to 1. We're going to go from dimensions equals 2 to 15. Cool. So this, I love maths, but I have a terrible intuition for high dimensional geometry. This confuses the hell out of me, right? Like if I plot this, what I'm plotting is, this is the ratio, it's like the volume of the sphere to the n cube, If you go up in dimensions, can anyone look at this plot and tell me what's going on? Like, it's kind of surprising to me, but maybe, yeah? Yeah, and but look at the shape of it. Yeah. The thing that does my head in is look how it's dropping off as you get big in dimensions. So the ratio of the size of this ball to the cube is way, 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 way bigger than the ball as you go up in dimensions. Like it's mostly the corners of the hypercube in 15 dimensions. So I can't do pure maths is awesome because you don't have to think about that stuff. What's that? Oh, it kind of just keeps getting smaller and smaller. So if you plot this on a log scale, you see something, it just keeps.
It's not what you expect.
I don't expect that because I'm a three-dimensional monkey. I can't think in 15 dimensions. But like, yes, if I think through the maths, yeah, it totally makes sense. But to me, it's super surprising. So consequently, if we're doing this Monte Carlo estimate, the probability of getting a point inside the actual sphere gets really, really, really small as we go up in dimensions. So super surprising. So what we're going to do, I'm going to run this. So this is running the Monte Carlo estimate. So it was quick, ran through all those dimensions pretty quick. I fixed the computation budget. I can't remember what I said num samples was. I think I did 1 million. So if we plot that on the same plot, that's what that guy's doing. See where this goes. Hey, that looks way better than the other plot. So it's starting to get a bit ropey as we get up to 15 dimensions, but I fixed the compute budget at 1 million points. If I bump it up a bit, it should get a bit better. If we want to see, you know, this would be the one to make us feel better about ourselves, we do this guy. So this guy's going to chug, chug, chug. It's go through. And look at that, state-of-the-art cubature integration method. Completely loses the plot beyond like 5, 6 dimensions. But the dumb thing of just go like throw stuff out and see what sticks works all the way out to 1 million dimensions. You just have to scale the points. So Monte Carlo methods, super powerful. Being able to draw random numbers in these randomized algorithms are surprisingly good approximation schemes for integration. Cool. Any questions on that? Yeah.
How would you explain why the Monte Carlo method is better?
I wouldn't. It's beyond me. That's another course and completely.
For this particular problem, why does it work more with this?
Well, it's that thing of like, what does fitting a surface mean, and how stable is this surface fitting thing? It's more like why does the other one perform so badly? Is probably the real way to think about it. Yeah, these like, you know, fitting a polynomial to 2 points, 3 points, that's okay. You're fitting this arbitrary surface. Does that do a good job in high dimensions? No. And how does that scale with the size of the problem? Not so good. Yeah, so yeah, think like, in particular in statistics, has anyone heard of MCMC? You have? What is it?
Well, basically you have these random chain things. So you're trying to sample a probability distribution.
Yeah.
And you have this little walker that sort of bounces around.
Yep.
And there's a weird criteria that I can't quite remember.
Yeah. It's
basically, instead of going all the way to the center, it bounces around a bit.
Yep.
And so it basically comes up with like a visual idea of what the distribution looks like.
Yeah. So MCMC is the super powerful version of this. So it's like there's this acceptance criteria in how you do the sampling, but that's like state of the art for doing this high dimensional integration stuff in statistics. Really powerful, really powerful method. Really cool. I think I just plotted the absolute error as the only bit to go with this guy. Just if you don't believe me by looking at that plot, different alternative plot. So we just go like, look at how the relative absolute error for the Monte Carlo method scales with dimension versus the cubature method. So again, cubature method actually flogs it in low dimensions. You'd be silly not to do it. you know, to do this polynomial stuff. But there's a critical dimension where it'll flip over about 4 or 5 dimensions, and the Monte Carlo one starts winning by a long way. Cool. Surprising applications of that. Okay. A little bit more time. We'll go. Okay. So differential equations. So this, you know, can't overstate how important differential equations are. If you're going to say, you know, be rude and say physics is just the applied bit of differential equations, and that's all it is, right? It's like mathematics is this huge thing. Physicists are just mucking around with differential equations. So you can't, you know, and engineers with that one too. So like, it's a big field. Given you in the homework, we've given you a little example of like a couple of simple ones. And again, the educational point of those questions is this worse is sometimes better, depending on the problem. That's the whole point of like question 16 versus question 15, if you want to hint. So question 16, we've done this leapfrog method, which is kind of naive and silly, but for that particular class of problem works really, really well. Yeah, so again, it's really, really simple. Again, to this definition of a derivative we had back up here. That's not the best picture. I won't worry about talking about that. Basically, oh, it's this one. Let's go back to here. These notes are out of order. So basically, you know, a differential equation, you're going to relate the derivative of something to some function, right? And then you're going to solve for the function itself. So basically, the dumbest thing you can do is, so if I have some general differential equation, let's just go over here. So f dash x equals some function of x and maybe t. That's it. So all we're basically doing for the dumbest version is we're going to put in approximations for this derivative and then solve them. And for initial value problems, they end up in these iterative schemes. So let's just do it. This is the worst tool for doing this. That's not what I want. So we've got f dashed x approximately equals f of x plus dt minus f of x. You know, that's dt. That's kind of like the dumbest version of this derivative approximation we could do. If we plug that in, we'd get something like, what we want to turn f of x plus, I'm going to get this wrong because I didn't write it out beforehand. So I'm plugging it into this equation and rearranging. So what will that do? I'm going to have a dt times y of xt. It's not an 8. And then I'm going to, so that's taking that bit over, and then f of x. Be something like that. Oh. Sorry, what am I doing? I don't want to f dash. Why do I call that y? What am I doing? X dt. Let's do it that way. All right.
We can't actually see.
Oh yeah, I think it's a loss anyway. Okay, let's go that way. So dx dt. I'll just start again. Sorry, should have pre-prepared. So we've got some dx dt. Dx dt is some function y of x and t, and we can approximate dx dt equals. What am I doing? Let's go. No. I'll go to the notes. This is terrible. Okay. We must have it here in the notes, so I don't have to type that again. Okay. So yeah, here we go. This is what I wanted. I was trying to write it out. I couldn't see it straight away and I panicked. Okay. So we've got some dy dt equals f of y and t. And we've got some initial condition for some t where we know what the value of this thing is. That's the setup for the problem. So this is initial value problem. So we want to know solutions from t out to t equals infinity. And what we can do is we can write out an approximation for this thing, where we're going to go take a small step in time, and this is basically what this derivative is. And then if you plug that guy back into here, which is what I was trying to write on the other one, you end up with this really simple thing where some value in the future equals the previous value plus time step multiplied by function evaluation. That's Euler's method. That's the dumbest one you can do. It's really simple. And then you go, cool. If I want to step forward, I just march through, keep reapplying this thing. I get a thing at every next time step. That's the dumbest one. That's the dumbest version of this thing, Euler's method. So I don't think I want to say too much about that. The tension here, I guess, we were talking about this floating point thing here where we're going to go like, hey, oh, this sucks. If we get really small h, we're going to get really bad problems. Doesn't tend to be so much of a problem with these differential equations, numerical solution differential equations, because typically you're trying to take big time steps because you don't want it to take forever. So this will be linear in the number of time steps, right? So if you're going to set your resolution in time really, 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 really small, it's going to take forever. So the game with numerical solution of differential equations is you want to be able to take big steps in time. So not so much of a problem, that floating point thing. Yeah, similarly to the numerical integration scheme, you can do these intermediate point methods, which is basically, you squint and you can sort of see the echoes of Simpson's method there with the coefficients. It's like, it shouldn't be too surprising because, integration is numerical anti-differentiation. Is anti-differentiation. So there's kind of this one-to-one, and there's this hierarchy of methods of these things with these intermediate points called Runge-Kutta methods for these types of polynomials. And there's an actual zoo of numerical methods for numerical integration. Yeah, I don't want to say too much about that. I'll probably say just the little point is to do with the home. As everyone started the homework and had to go at this one, 15 and 16. Any questions in particular? It's 16. 16 is the bit I probably wanted to say about now. Let's go to that guy. Okay. So again, this generalizes to n dimensions. So I've given you a problem that's a little bit higher. What we've got is for a single planet, we've gone, okay, cool, force, every point is interacting with every other point through gravity, and it's got this inverse square law between them. So they're all attracting each other. If I solve that, I end up with this system of second order differential equations. This is probably, I'm going to say it really loud here. There's a system of second order differential equations here. You can turn that pretty trivially into a system of first order differential equations by just going, dy dt equals vy, dx dt equals vx, and then this is just plugging that in. This one is directly amenable to Euler's method. You just kind of go like, the right-hand side is the function, the other side is the vector of derivatives. And you can chug through that and you can see. And so generally what you'd expect is that these higher order methods will do better. The problem is though, that there's a special property of this thing is that this is a conservative system. So I don't expect you guys to have done physics, but this system shouldn't be losing energy. And doing it with these, Runge-Kutta type, Euler's method is the lowest order method, but Runge-Kutta type methods, they don't conserve energy. So there's a special type of integration you can do called leapfrog method. If it's a conservative system, which means you can write it as a system of second order equations in a special form. So maybe like that guy. So please look at that system of equations. Don't worry about all the Hamiltonian guff down the bottom. It's basically like plugging this guy into leapfrog method and see what happens. That's what I'm going to do. This is like taking advantage of this special property of these things called symplectic integrators, and symplectic integrators conserve energy. So if you're trying to do something like solve for the planetary motion for a long time into the future, preserving energy is probably a really good thing to do. Okay. what can I show you there? So I probably think this is good to show. Is this coming up? Okay, I made my life hard when I first did this question, and I did it for a 4-body system. So I did the same thing, but for 4 bodies, okay? This is the reason you do numerical integration, because this is a surprisingly simple system that exhibits very, very complex behavior. So I gave you the easy version where it's just 2 things, and they pretend like they're just a second-order system, and all you're going to get is conic sections, right? So that's the classics for this system. If you go up in dimension, it actually becomes a chaotic system. So I've given it a kind of pathological initial condition in this case, where they're in an unstable equilibrium. And these guys will chase each other like crazy worms. So this is, to me, very surprising. It was really surprising to people doing differential equations like 19th century, that you can get really, really complex behavior from a really, really simple system really easily. And analysis is gone. Like, what's your chance of deriving an equation of motion for these guys? Like, it's impossible. All you have is numerical methods. So if you're sophisticated, which I'm sure you guys are, do you believe me that this is real, though? What could be going wrong in this simulation? Like, if I've got something that looks pseudo-random, what could that be? What could be the cause of that? I talked about it like all last lecture, like half the last lecture. Floating point. So is this real? Is a real question. Like, so again, we need the pure mathematicians back in the room, because we've got to work out, is this real or is it an artifact of the numerical simulation? And I hope you guys all have the sophistication. If someone says, oh, I've done a simulation of blah, is it real? Is it floating point stuff? Were they careful with how they did all the numerics? Because you can get surprisingly complex behavior either from the dynamics itself or because you did it badly. And it's really hard to tell the difference. So this is one of these questions of like, so to the room again, how could you verify the accuracy of this method? Like, what's the simple thing you can do? If you don't have access to the solution, what's something you can do?
You could try shift movement system, so like floating pairs would be different.
That's an awesome answer. Yeah, good. That's great. That's the, yeah, it's cool. Translate the problem in a trivial way, see if you get the same answer. Anything else you could try? Step size, step size. Step size is the big one I'll be looking for as well. Do it on a different series of step sizes. What you would generally expect is that as dt gets smaller, you should converge towards the actual solution. If you're getting a wild solution with step size, like if it's going to something strange, you know, you're probably not seeing anything real. That's another thing you can do. But okay. All right, that's probably a good time for a break. Feel free to grab chocolates if you haven't had any, or even if you have had any. I'll take a break for 5 minutes.
Yep. So just more like sort of what you thought, like it says to like figure out what the ideal H is. Should we just be looking more like because there's some weird behavior where like the main peak is here, but you've got a few things to the side.
Yeah,
really
I'd be kind of like
it's where the
crossing
main-
my eyes. And
Yeah,
thinking
yeah,
through
okay.
the door.
Yeah,
It's kind of hard. Like if you think about it as risk,
yeah.
like if you got it slightly off, would it be as important?
Yeah.
That's about it. But it's again, it gets really floppy really quickly. Yeah.
Thank you.
Yeah, that one's disappeared.
Oh, did it? I can't understand why. Hello.
I did the previous and I can do it in a long time, but I can do it. I was just wondering about the stuff, like just sort of the bitwise and stuff. I understand how it does it, and I don't understand like.
Sorry.
I don't know if I've seen any of these, but the idea is that each of these like digits will not be like greater than 10, because otherwise it's like, you know, it should have been.
Yeah.
And so this question down here is like, okay, throw an error so that if any of these are like full bit,
or greater than 10.
Yep. Okay, so the solution said if D is greater than or equal. I don't understand how that translates to like coding.
Oh, wow.
Maybe
Okay.
throwing a lot of something in your face.
No, that's cool. D equals BCD. I'll take, so you take BCD as the US. Mean question. I'd be sad if I got that. Okay. Okay, yep.
It's not. So it's just at the same time. He's good.
Okay, so that six string. So D, BCD, and X. So what does that do? That line should do. What's that?
I mean, I know that that's hex for 15. And that's
Yes,
Okay, so what does it actually? So this is coming in as a UN 16. So it's
undeniable. And then it's gonna go outside. You need to.
I'm confused by that one. It's doing.
the line's
Oh,
like,
okay.
it's supposed to change. So that's what you'll be changing to like.
Oh, okay. I'm just looking at it. Going, that's
Yeah.
busted. Okay.
Like what's
Okay. Yeah. So that would always throw. That's what I was looking at going like, oh, that always throws. So that line, if you ran that function, it just throws. Okay. Okay. So your question is like, what's up with
Yeah,
one?
how does like that sort of translate to this is the size of the image? It's not.
Yeah. Okay. So a UN 16, you'd have to look at the representation of a UN 16.
Yeah.
So yeah. And what was the number? And OX. Or how many zeros? So I guess what does it do for 11? I got to think that one through. Yeah. It's a good. That's a hard one.
Yeah, I was thinking.
It's not how I. It's hard when it's not how you do it, right?
Yeah, so much of this, like I can do math.
Yeah.
Okay.
Let me think about it. I'm a bit thrown, but yeah. Hello. Yeah.
Quick sort. I mean, having so much difficulty. Like whatever I do, it's always been slower than I will sort of do.
Okay.
And I got advice from a tutor that it's probably how I'm choosing the particular like
Yep.
that's the right stuff. Just don't really know any other ways to because apparently I haven't unlocked the true efficiency of quick sort.
Yeah. So the usual one, I think I said this in the lecture, is like you can get the worst case for the. I think the worst case for the pivot strategy, but given you is if it's already sorted. So be careful that it's not already sorted. But I guess
I did timing stuff at the end where I would try this in between.
okay.
Like I'd reinitialize the
Yep.
and it would give the like the starters to if I just do that. This loop will not start. But I've tried this. The timing's always it's weird. Even though it's sort of random data.
Obviously, no allocations. That's suspicious to me.
No, I'm actually. But I'll let you check it.
Yeah, check.
Okay.
It's suspicious.
Bubbles that's not being used.
Yeah, like if you know where near your inbuilt sort, that's not surprising.
Yeah.
But yeah, and the
I
big thing to
thought
check is
do that actually. I always do the same thing. You know, I'll check that.
yeah. Okay, no worries.
Okay. All right. Back to it. Okay. Hope you all got chocolate in the break. Okay. Where are we at? Where are we at? So it's like the quickest run through of differential equations you're ever going to get. So that's fine. You're all really smart. You'll catch up with it. I'd just say as well, I guess part of question 16 is learning to drive an API. It's really important. So typically I don't write everything I use. I use someone else's stuff who's smarter than me and spent more time testing it. And you get this like, again, I was trying to say, it's kind of weird in an academic environment because like, don't cheat. And then when you get out in the real world, cheat as much as you can get away with. As long as you're not breaking the law, it's fine. Yeah, using other people's stuff is like a superpower. Like, so big part of it is learning to use someone else's code, working with other people's code. It's fine. And this is like one of it's a really good package with probably a terrible API that's hard to learn for differential equations. You got to, well, a part of maturity with this stuff is learning to adapt to other people's stuff and understanding why they did things a particular way. You can actually learn a lot from your implementation of things if you go and look at how other people have done it. Differential equations is kind of state of the art. So it has things in here that kind of don't exist in other packages. So it's worth learning. Yeah, differential equations, really recommend it. It's very, very good package. Again, it ends up being, like I said, we give you this introduction in the notes of a symplectic integrator. It's this case of worse is better. You do this really simple thing, but because it conserves energy for this particular problem, where it is conserving energy, it does a lot better. So planetary motion, you know, it's just, yeah, no dissipation. So you can sort of know what the energy is going to do forever. Yeah, differential equations, totally recommend it. Very big package, takes a while to build. You probably noticed that. And there's a zoo of methods because, again, this always happens that the details of the method matter, you know, so you kind of have to know a little bit about your problems. And some of these ones that'll happen are there's certain physical systems that have very, very different time ranges. So one of them's, if you're thinking about physics, would be like if you had a shock, like they do hypersonics just over the road there in engineering department. If you're breaking the speed of sound, you're getting this basically a discontinuity. So if you're thinking about what sort of time step you need to use for integration, it's like changes really, really, really quickly. So having methods that can deal with shocks is a big deal. So you get this whole class of shock capturing methods for differential equations. So you kind of need to know a bit about the system to pick which is the right one to do. I don't know if I want to say much more about that. And then, okay, then partial differential equations, the whole other beast. It's even worse. It's a great field to get into. I really love numerical methods for partial differential equations. You get very confusing things. So I said this hint about like, you know, a little test you could do for the error is shrink the step size. And if it sort of converges to the same solution, like, yeah, that's a good job. In partial differential equations, it's completely possible to have a thing that converges nicely to the wrong solution. So it lies to you and looks like it's going to the right solution, but it's going to the wrong one, depending on the numerical method. So really fascinating area and super important. Like I said, this is basically like a big part of applied mathematics is differential equations, and this stuff matters. Any particular questions about that stuff before I move on? Yeah.
What you gonna do is with that we had to pick methods. Is there any way to like kind of guide our selection of the methods?
Second order. I was trying to like hang over this thing and going like, don't try and plug the Hamiltonian in, plug in the second order method. So if you're going to the quiz question, you're gonna go like, cool. which one should I be doing? I can never find where this thing is in the course because it's in a strange spot. I think this is like me trying to be a bit cruel. And I've given you a whole bunch of extraneous information that'll just lead you astray. Don't worry about the Hamiltonian stuff. You know, that's just to convince you that it is a Hamiltonian system. It's really this second order form. If you can find a second order form and you just plug it into leapfrog method. So if you look back up in the notes in here, we've given you the second order form here. So it's basically just like plugging those guys in. It's like when you click about what you should do, it ends up being like 5 lines of code. It's not much code at all. Question for you as well with scaling, because like this is the thing I was trying to go through with sorting. If we have planetary motion, how do, gravity works on everything, attracts everything else. How does that scale with number of celestial bodies? Like if we have the solar system, I don't know what I want to say, is there 8 or 9? 9 will do. Depends if you count Pluto or not. Oh, the sun too, there's 10. So everything's attracting everything else. So how does this system of equations scale with n in this case? Yeah.
Is it n to the power n?
No, it's not that bad.
Because you're approximating those points. Whereas there are tons of situations where you could rip a planet apart by like taking 2 units sun or something.
Yeah. So that's right. So everything attracts everything else. So naively, everything's n squared in this case, not n to the n. That would be awful if it was. So I guess the thing I'm trying to get you guys to think about is like, which is to your answer of like, how do you simulate something like a galaxy? Like, I don't know how many stars are in a galaxy. Does anyone know? It's a question for physicists or astronomers. Too many, right? Too many. So what can you do to get something like this to scale to larger and larger systems? And people do simulations of galaxies. I'll get a supercomputer to do it. And the trick tends to be this thing of like, how do we dumb it down from a system of points? Like if I'm over here and there's a couple of points over there. Yep.
It's kind of like you want to approximate like a field.
Yep.
And then it's simply gravity affects the field, and then you calculate how that field affects each of the
That's one way to do it. They actually do the other way too, where they'll do it's called the fast multipole method. So that's another way of doing it, where you can turn a set of points to an effective point at a distance. So they do both. It's kind of cool. Yeah, that's the way to think about it. So there's still a lot of analysis in the numerical solution of these systems of equations. Hey, Yoni. Cool. And practical too. Okay. That was just to do with 16. Okay. Okay. All right. How much do I want to say about this last two? Okay. So last one is like, I wish I'd learned more linear algebra at university. I think Yoni and I were talking about this the other day. It's like, I kind of afterwards, I had to learn all this stuff. It's like, it's super powerful. Linear algebra is super powerful. Like all the good stuff's in linear algebra. Like your job as an applied mathematician is like, if you can turn it into a linear system, kind of good to go. Because it's like, there's lots of good methods, there's lots of good results you can use. Trick is, how do you actually do that embedding to turn it into a linear system? Yeah, linear algebra is a thing you have to import. So it'd be like using linear algebra. It used to be in base, not so much anymore. Yeah, again, I'd make this point of like, what's Python for a scientist without NumPy? Like, it's kind of nothing, right? Like, it's so useful to have linear algebra, and it's nice to have nice syntax for linear algebra. I guess it's well beyond this course to go into all this stuff, but vectors and matrices and doing certain types of factorizations on matrices to come up with things. I gave an example of computing eigenvalues. You have a question in your homework about eigenvalues. That's a super relevant one. I don't know if this is apparent to you guys or not, but application of that, the question where you've got like the Markov chain, you're going to like jump around. Does everyone had a go at that one? Well, does anyone know like what's the That's like $1 trillion algorithm, I would say. Does anyone know why? Anyone familiar? Little company called Google, PageRank's original algorithm is basically what you're doing for your homework, is how that works. So again, super powerful thing, if you can turn your problem into linear algebra, you can use all these powerful methods. So basic idea, again, I'll just motivate it by your homework. You know, here's a really dumb model for the internet, right? I don't know how many web pages are on the internet now currently, but it's a lot. Back when I was younger, it was a lot less. But a simple model for the internet, a person browsing the internet would be, I've got a bunch of sites I can visit and they have links that link out and they link in. And I'm going to come up with this really flattering model for a person is that they just randomly click hyperlinks with some probability, right? And then randomly they'll jump to some other site, like they'll teleport. And that's the model for the original PageRank algorithm for Google. And it's this Markov chain thing where you're going to go like, I'm randomly clicking links. What's the stationary distribution of where I end up? If I sort that in order from the most probable to the least probable, that's PageRank algorithm. Done. It's pretty straightforward, right? So $1 trillion algorithm you guys get to do for your homework now. If you'd only done it 20 years ago, might be in a different spot. And again, that's to do with, you know, you've got those 4 different methods for solving this. There's one based on linear algebra, one based on simulation, one based on eigenvalue decomposition, and one based on repeated multiplication. Is that correct? Did I get that right? Pretty much, pretty much. Which I guess this is going to go on to the second bit of this part, but so do you think it's possible to have that transition matrix for the internet? Like how big is that going to be from every site to every other site? So which of your 4 methods do you think is practical? Then you understand why it's $1 trillion algorithm. So if you want to think ahead about how that might work, how do you store that transition matrix? How do you actually do this stationary distribution calculation? That's kind of where it's going. So that's the motivation for learning about linear algebra. Again, science, like we just talked about partial differential equations. Most of the time, if you turn the finite difference approximation for a partial differential equation, you'll end up with a particular banded matrix structure. And solving those things is basically how you do solve partial differential equations. There's a million ways to do it. Again, we showed you this stuff earlier on. If you want to set up a matrix, it's got, I don't know if it's great syntax. It's hard to write out lots of them. But, you know, spaces for the things on the same row, then go, oh, so yeah, on the same row, then to go down to the next row, you put a semicolon in. You can do it of all different types. You could do it as floats. You just promote one, they'll all end up as floats. You get the shutters when you see inf. If you do numerical stuff and you get very, very scared of inf, like the way to solve linear equations is not with multiplying by the inverse. This is a 1 point for the second half of this lecture would be that one. You do not multiply by the inverse. It's not the stable way to do it because of floating point stuff. So someone, I think it was you, said a really good question, really good statement at the end of the last lecture of like, how does anything work with floating point? This is the case, right? Where you've got to be super careful about propagation of errors, and solving linear systems is the big one. Yeah, so you can calculate an inverse. If you want to set up, this kind of a cool one. This one might not seem immediately apparent, but why this is great. If you want to set up an identity matrix, you do this thing called uniform scaling, and this is actually super clever. Just in case you're not clear what A was, and we're going to subtract off uniform scaling. It doesn't actually allocate anything. So uniform scaling, I don't have to make this huge matrix of like zeros with 1 down the diagonal. It's just going to apply it because it knows the type. This is one of these magical things with Julia. So if I look at the size of that thing, it's kind of just like pointing to a special type to apply to functions. What do we want to do? So this one, linear systems of equations come up all the time. I guess Megan came in, she's talking about Fugro. That's part of my history too. Fitting quadratics to LiDAR points for power lines. That's like, I've done so much of that. So you get an idea of like, if I have some points, so let's just do it. We'll just make some random data. We've got 100 points. Okay, and then we're going to go y equals 2 times x squared plus 8. That's not what I wanted. Plus. I had a function called y. Okay, that's annoying. Plot x, y. Okay, that looks pretty terrible. So let's go for a scatter plot instead. Okay, so that's the kind of thing you would see at Fugro with Megan. You'd go like that. And then typically, because it's real, you'd get some little bit of fluff on it. Size of x, 0.01. You know, that's like, it's kind of like real data now where we've sampled something and it's got a bit of noise on it. If you want to turn this thing back around, we've got a linear system in the coefficients. So the typical thing you would want to do is we'd have a matrix that goes like A equals 1s, length x, x. Okay, so what we're going to do is we've got a polynomial, we're going to try and fit the polynomial to the data. So this is a thing called a van der Mon matrix where we've just gone like, if it was a polynomial, you'd have a constant coefficient, some term on the power, the first power, and some term on the second power. So yy div 8 should give us something like, oh, did I get this right? This is going to be the problem. Sorry. We said y equals blah times x. So this should have something like y equals a times x. We just don't know what or some coefficient, sorry, a times some coefficients. We've got some values we're trying to solve for. So we've sort of sucked those into this A matrix. So what we're really trying to do is we're going to try and solve for the coefficients beta. All right. So that should be A div y. There we go. So that's this magical algorithm by this thing. And we've just used, this is a bit of magic Julia syntax that we've gone, okay, cool. We want to, it's kind of like dividing, but for a matrix. Slash beta equals A back divide y. Cool. If we look at what we made this with, hopefully we're not too far off. We've got the first coefficient is 0.02, 0.02. Because of numerical error, we've made a bit of a misestimation of that second coefficient. Same with this one, and we've got a +5. So we've managed to get these coefficients back. Super useful, fitting a quadratic to noisy points. That's kind of like, that's the easy version of Megan's job. It's like, if you just had the points on the power line, then you can go sell that to the power company for $10 million a year. Problem is finding all the power line points alone. That's the biggest part of their job. So that's a motivation for linear algebra. And it's deceptive, right? Like all I did was this guy. And it's like, cool, what's that thing? Like that is horrendously complicated underneath the hood. So if it, depending on the type of this thing, you know, if it's just integers, like, yeah, cool. That's nothing special. But if we're talking about matrices, it's matrix division using a poly algorithm. So this is an algorithm of algorithms underneath the hood, and it's incredibly complicated. So depending on the type of the matrix A, it will do different things that are appropriate to the problem. And this is kind of getting around your question before about like, oh, there's all these methods. What do I do? This is much more developed algorithm where they've gone, hey, I'll figure it out for you and I'll do a better job than you ever will if you're picking yourself. So underneath the hood, lots and lots of years of experience, like depending on the type of the matrix, it will do different things depending on the structure of A. Again, can't overstate, floating point is a big deal. This is all dealing with different types of matrix factorization. So we've given you a couple of examples here. That's another version of the fitting. if you want to go through. So if basically the thing to remember is if it's overdetermined, you really want to be solving this. The minimizer is the solution to the normal equations, and this guy is doing that underneath the hood. So you don't even need to worry about that. And again, we've got a bunch of different ways that you could approach solving this. I'll let you go through this yourself, but you know, solving it via the normal equations, if you wanted to construct that by hand, you can do that. You can solve it the bad way by doing this multiplied by the inverse, which is going to be really horrible for floating point. You can do the pseudo inverse, Moore-Penrose pseudo inverse. You can just do the one I would recommend, approach F, which is the one I just showed you, where you go like, let the algorithm work it out. You can do these factorizations by hand. Like if you know a little bit more, you got a special sort of setup for the problem, you can do the factorizations of this matrix. So one of these guys is this thing called a QR decomposition. Lots of notation there about what's going to go on. They don't know much more about this than me. Basically, you're going to turn it into, there's these two, a Q matrix and an R matrix, and I think that's an orthogonal matrix and an upper rectangular matrix for this guy, but details. It just, doing this factorization, doing the inverse becomes easier and much more numerically stable. And this is how, kind of what it's doing underneath the hood. We've got this thing called a singular value decomposition, which was where I was going to run into next. Just as a little example of image, I talked about Fourier transforms. So I was going to talk a little bit about image compression with SVD as a little demo for you guys. Cool. So a whole zoo of ways you could solve this thing. I think I'll do this one. So I have this guy. Okay. So anyone heard of singular value decomposition before? You have? Do you want to go for the explanation?
I saw it last year and forced by camera.
Yeah, it's super confusing. I keep wanting this one word explanation for it. You go look at YouTube videos and they go like, oh, it's like a rotation. It's like, it's not really. The way I think about it is I think of it as an approximation via outer products for a matrix, right? So if you think about it as like a greedy algorithm for, like I've got some non-square matrix and I want to approximate that in terms of outer products. So this is, you've got this in your homework question too, of like various dubious ways to do matrix multiplication. One of them would be via outer products and summing them together. This is kind of what an SVD does. And that's the way I think about it. It's kind of like a variational way of thinking about it. You go, if I wanted to form, you know, if I wanted to approximate a matrix with one outer product, what would be the best way to do it? And then if I wanted to do it as a sum of two outer products, what's the next one? And what's the next one? What's the next one? And this gives you like a little lead into machine learning, little lead into like how much information is really in data and how do you represent things? And it's kind of a famous one. So I've got an image here. Just a random one I took somewhere. So that's an image. It looks like lots of stuff's going on. Images underneath are just arrays, right? So we talked about this. I think it's good to show you. So we've got this image, and I'm going to load this image. Okay. Type of big. It's this funny matrix of RGBs where it's this special normalized float 8s. Right, so here's a float 8, which is kind of weird. We'll talk about float 16s. So they're not really float 8s. What's this? No, so it's a normed uint 8. That's what that little F8 is. Sorry, I forgot what it was for this library. So the uint 8s, so each color, R, G, and B is like one bit of these pixels. Each of these images is an array, and they've all got three values, an R value, a G value, and a B value. And so each of these pixels in this image, that's all they are. So yeah, that's that image. That's all the pixel values. That's all they are. An array of three things. So it's pretty big. So I'm going to resize it down by a quarter, just so don't crash out my computer. They're actually big, right? Like, so in big, this image from my old smartphone was 3000 by 4000. So as a raw image, that's huge, right? Like, so that's going to be, if that was float 64s, 4032 times 8, big number. No, it's 88. What am I doing? Yeah, big number. So your phone would fill up really, really quickly if everyone was that many megabytes. One photo is like 100 meg. That would be crazy. 64, really. Sorry, even bigger. Huge. So it's 780. They're not that big, right? Like, so what's going on with actual images that you can get these things and they're not so big. So what I'm going to do is split those into channels. This is this Chan view. So just to be clear, let's go size of this guy. Can't type. Anyway, that's not helpful. Anyway, what I'm going to do is this is a multi-dimensional array, each of these channels. So we can get the red channel, the green channel, and the blue channel by slicing on this index, the first index, second index. And what I'm going to do is I'm going to do this factorization that turns it into, if you want to look up what an SVD does. SVD, what it does, basically what you said, is that there's these three, it breaks it into these three matrices. There's a U, an S, and a V, which kind of does my OCD, and it should be an S, a V, and a D, but they always call it USV. So these are orthonormal matrices, and this is a matrix of diagonal values, which are kind of like square root of eigenvalue, pretty much. You can think of them that way. So this is a really useful decomposition if you can use this as an approximation scheme. So what I'm going to do is I'm going to do the SVD on each of these channels. It's reasonably quick. SVDR. You'll see you've got this S matrix, which is the singular values, the matrix of singular values, and you've got this U and this V and this orthonormal property. Look at that wrong. Oh, anyway, we'll show that later. Okay, so we're going to do the SVD. So interesting thing is if we look at these singular values, we can see that they decay super quickly. So they almost all do the same thing. So really interesting thing about images, because we've got color information. Both of my kids, both my boys are colorblind, which is kind of interesting thinking of this, is there's actually not that much information in color channels, which goes to my day job, which I might get time to talk to you about. There actually is, but not for humans. If you're doing a machine learning thing, a grayscale image and an RGB image basically have the same information in them. There's not that much extra there. So the mutual information between all these channels is there. And if we're thinking about this as an approximation, SVD as an approximation scheme in terms of outer products, most of the information comes in really quickly, and then we've just got like noise down the bottom where it's junk. The way to show this is this thing called the trace norm identity. Recall, I say, you might never have seen this thing. So if I say Frobenius norm, does anyone go, what the hell's that for? You do? Anyone know what it is? Anyone know what it is? Frobenius norm? Basically, if you think of a matrix and you kind of turned it into a big vector and you go like the L2 norm of that. So like sum of squared values of that. That's the Frobenius norm. Does that make sense? No? Yes? No? Happy, not happy? Somewhat happy? Yeah, just think of it as take your matrix, turn it into a big vector, take the L2 norm. That's the Frobenius norm. And this identity is that the Frobenius norm equals the square root of the sum of the singular values squared. So you can think of like, yeah, pretend I've got it here, it says it here, Frobenius norms, pretend matrix is a big vector and take L2 norm. So this kind of gives you this hint that if I truncated the singular value decomposition, maybe most of the information's in these big singular components, this big singular values, and I don't have to worry about it. So here, this is the This is the proof of that trace norm identity. Proof demonstration. It's not a proof. So if we look at the norm of the channels versus the norm of the singular values, that's approximately true. So that's just like we're taking that original matrix, we're going to calculate the norm of that, the Frobenius norm, sum of the squared values. Most of that information is captured in this guy. So what we can do is I've done this thing of low rank approximation. And what I'm doing is I'm going to take this U matrix up from 1 to K. So I'm going to include K values of this. I'm going to take the diagonal value of this SVD matrix up to K and also this V matrix. So if I took all of this, it's just like taking the SVD decomposition, multiplying it back together, and I get the thing back together. So let's just see if I can do that. Dot U times, this is what I was doing wrong last time, SVD S times SVD dot V transpose. Cool. I'm not happy there. Oh, because I've got a diagonal this one. Thought I'd done it. There we go. So that should just be like reconstructing this red channel back from the original one. So that's this one. So what we're doing is when we're slicing this, SVD colon comma 1, like in this guy, the U colon comma 1, we're just going to slice out the first column, first row, multiply them together. So that's going to be like an outer product. Hopefully that's clear. So that's this low rank approximation. So this thing is going to be much, much smaller than the original image. Like if I'm just going one vector by one singular value compared to the whole matrix. So it's much smaller. So if that could represent the whole matrix, it's like, cool, I don't have to do all that stuff. I don't have to keep all that stuff. So what I'm going to do is, what does this approximation error look like as I vary the number of singular values I include? So here, so this is this approximation error. So like with one singular value, I get like 70-something% of the image back in terms of the Frobenius norm. Then as I add some more and more, it goes down to almost 0. So if I include like 60 singular values, I get almost all the image back. Cool. So there's actually not much information in this image. If you think about how much information there could possibly be in an image, you know, like if I just look at random, totally random image, you wouldn't see this property for the singular values. That'd all be a straight line because it's just noise. But this is kind of where things like statistics and science are coming in. It's like there's not actually much information in all this data. It's all kind of like hidden in one corner. And if you could just find where that corner is, it's like that's where the real information is. I'll give you what this actually looks like in terms of what we're doing, because it's kind of more obvious if you do that. So this first one, what I've done is I've done this outer product with like one singular value, 10 singular values, 20, 30, 40, 50 down the bottom. So this is just like, this is a thing of like, you get 70% of the image back by just doing one outer product. And then you fill in a bit more detail, and it looks really blocky because it's an outer product, right? Then you do 10 and you start seeing the clouds look a little bit better and you start to see the trees. And then by the time it gets up to 60, you know, cool, it looks pretty good, right? So there's not really much information in there. I'm just using linear algebra to pull it back out. Okay. This is the thing I was trying to do originally. The original image, full size, is like 36 meg, which is massive. But cameras, you know, if I take a photo, my phone's going to be full really, really quickly. If they'll float 64, it would be even worse. So don't do that. So you can calculate the percentage reduction. Like if I'm just doing this thing. Let's go. I don't really need to do that. Yeah, so if I wanted to get 1% reconstruction error, I could make it half the size. So like that's in terms of L2 norm. That's what I was trying to do here. So when does it cross 1%, this reconstruction error? It's like I have to include half the singular values, pretty much. So yeah, so if you wanted to get it to like 1% error, you can keep half the singular values and you get a reasonable compression algorithm. Cool. How big are your phone photos? Does anyone actually look? Like in JPEG. Let's go look at this guy. So magic, 3 meg. So JPEG with FFT, fancy algorithm, compression, it gets it down to 3 meg. So we're saying we could get to 1% reconstruction error, we need to be 20 meg. There's this even better thing you can do based on Fourier transforms that gets you down to 3 meg. And it's probably better than 1% reconstruction error perceptually as well. Cool. That's a little demo. Okay, I guess I could talk about sparsity, but I think that's enough. Yeah, no, I'll skip that bit. Cool. I guess I'll use this bit to talk about myself as an ego trip. Yeah, I guess I am an accidental software developer would be the main point I would make to you guys. For anyone who's like, you know, should I be doing this as a career? I never wanted to do this as a career. I fell into it completely. My story, I guess, when I was in undergrad, I didn't know what I wanted to do. It's like the story of my life. I didn't know what I wanted to do. So I did kind of everything. And one of those was I did maths, I did physics, I did chemistry, and I did computer science. And guess the first course I dropped? Computer science, because I thought I'm never going to do that. I hate it. And then lo and behold, I went off. After undergrad, I still didn't know what I wanted to do. So I ended up doing maths and physics because I kind of thought I got really into differential equations. Thought that's fascinating. I'm really on the applied side, so I like the maths and physics, both of it. That's where I ended up. And then it's like, as I do more and more of that, it's like, cool, analysis is too hard. You need to do these numerical methods. So that's kind of where I ended up. Then, you know, maybe this thing of like, do you know what you're going to do with your life? I still don't know what I was going to do in my life. When I left uni, I was like, what do I want to do? And I thought, I started a PhD at University of New South Wales after, I grew up in Tasmania, by the way. So I should start with, I'm a bogan. I grew up in a town with dirt roads and no town water. I had tank water in a septic tank. So I'm a long way from there now. Yeah, so I got, my sister was the first person to get a bachelor's degree in my family ever. So like, I didn't even know what to do at university. So I kind of got to the end of undergrad and I'm like, what do I do now? And I thought, oh, I'm a bit of a hippie. I thought I'll work on, I saw this problem of working on reverse osmosis. Like I thought, oh, you can make clean drinking water for villages in Africa or something. And it's like, I did that for a while and I got kind of depressed because it's like, I think, has anyone heard that statistic of like, how much does it cost to make a cubic meter of clean water? Does anyone know? 80 cents. That's pretty efficient, right? So I kind of came to this conclusion that like most of these problems are political problems, not science problems. So if I do all this clever work and make it go from 80 cents to 70 cents, it's like, it's still really cheap. My PhD scholarship's worth more than that. You know, the real problems in the world are kind of depressing. So I kind of left the PhD. I went and traveled for a while. Didn't know what I was going to do. I came back. I did a PhD in, I kind of always back to dynamics. I was interested in control theory and dynamics. So that's what I did my PhD in. When I came back, I did another one. Then I left and then I did a postdoc and I did lots of interesting stuff. Then a friend of mine started working in a startup, which ended up being the place Megan worked at, which we were Rome's. It was just a startup then. I got bought by Fugro. Then I worked there for 7 years. And then after that finished, after they got bought, I'm kind of got like a temperament that doesn't suit well to corporate environments because I'm a bit too anxious and a bit too got to do stuff. Don't like the structure. So I left for another startup working with Andy. That's Samara's lecturer. Andy worked with me at Fugro, but I dragged him along to there. We were working on business optimization. He can tell you all about that. Worked there for 4 years and I've worked at a place called Plot Logic now. Maybe I can jump on here. I'll stop sharing here. I'll jump on here. see how this goes with my work computer. Sorry for that. Got it. Okay. So, where I work now, does anyone know what that guy is? Mantis shrimp. Does anyone know what's special about mantis shrimp's eyes? Yeah. So they see multispectral. So they can see more colors than a human can see. So I just said this thing of like, humans are terrible, like 3 color channels, they suck. Mantis shrimp, though, they're awesome. They can see way more. So I work in a company that does hyperspectral imaging. So instead of seeing puny mantis shrimp 16 colors, we can see 500 colors. So we have a special camera that uses a diffraction grating. So you get the light in, diffract it, we get this super narrow band color channel information up to medium wave infrared. So from 400 nanometers to 2,500 nanometers. Basically what we're trying to do there is we have a special camera and we look at rocks. I was never interested in rocks, but I got into it with this place. Geology is kind of interesting. Trying to work out what rocks are there. So again, I've got this kind of hippie streak of like, I want to help the environment. I don't think mining's going away, unfortunately. So what can you do to make mining more efficient? And it's kind of surprising how little information mining companies have about what's there. So they'll do these really sparse drills and they go like, we'll make a statistical model of what's happening in between. But when they get there, it's a surprise every time of what they're going to dig out the ground. So we're using remote sensing to fill in the details. So if you take, so it's a camera, it's a very, very fancy camera. So the back of it, to get these shortwave infrared frequencies, we need to cool the camera down to minus 130 degrees. It's really cold to get the sensitivity of the camera good enough to actually see this stuff. And what you tend to see when you look at this thing, if you get a normalized reflectance, is you get these characteristic absorptions. If you've done a bit of chemistry, it's kind of like to do with the modes of the molecules, like in a gas, that's what it would be. Like I drew this little picture on the side. It can flap like this or it can flap like that, and they have a different frequency. That's what these absorption spectrums would be. So you get way more information about what the thing you're looking at is than you would from straight color alone. So we look at these reflectance spectra. Tried to get a more representative picture of what that would be. So we get an image. This is an image of some dirt. I tried to make it look psychedelic, so you get this impression that there's more colors there than what you see. And this is what, if we picked on a particular pixel, this is what you see, this red thing. So you get these narrow band absorptions, and they're really characteristic of what's there. And we're trying to turn that into, this has got iron in it and it's got clay. So if you've got too much clay, please don't dig it because it's going to clog up your chute. That's pretty much what we're trying to do. So we take these images outside and try and model with the sun, work out what's going on with the sun. We get this false color RGB like this guy here, and then it turns into a field. This one's guessing how much iron is in places. So you're going to dig in the places you need to and not dig in the places you don't need to. This is important, I guess, environmental aspect, because like mining is really crude and it's like energy is really cheap and that's all changing. And how can you be more targeted in what you dig out the ground so you're doing less, less bad stuff? It's kind of a concern with, like, most of our customers are for battery metals. So all of a sudden everyone wants an electric car. Where does all the lithium and nickel and cobalt come from? It's like, you got to find that stuff. And so that's, in a way that's not, in a sustainable way, because we kind of made that mistake with petrol. Like, you've got to actually find this stuff in a way that's not too terrible. That's what I'm doing now. Career advice, I kind of landed here by accident. So I'm an example of, I fell in love with software afterwards. It's like, what you can do with this stuff is great. Particularly machine learning is fascinating to me. I'm the manager of the machine learning team at PlotLogic. Got a couple of people there, 6 people at the moment. The whole size of the company is about 70. So we do the hardware to software. So lots of interesting things. Just open the floor to questions if you want career advice from an old man that's going to be irrelevant. No, nothing? Doesn't have to be about anything important.
Was it managing a team? So you got 6 people. How much coding do you do versus management?
Yeah, That's difficult. So yeah, that's a typical thing is like, as you get older, there's this thing like everyone wants to get off the tools, they say, like do less coding. I don't get away with that. I wished I could, but I'm too productive. So I started as principal engineer at Logic, which is like, do stuff, all the time. And then I got a team to manage the team. It's kind of like, my ideal with this stuff is you hire good people and you don't need to do any management. So like, that's how I handle that. And whether I've done that successfully or not, it's a different question. You'd have to ask my boss. But yeah, that's kind of the way. So it's difficult. Managing people is the hardest thing, for sure. Alan?
How do you wrap up like a really, it's the very end? How do you like pull it all together?
We're trying to make software, so it's kind of easier. Like I have worked in more of that consulting thing where it's like, cool, you got a bunch of time to do something and you got to finish it and make it finish. And I'm actually terrible at that because I'm too soft. Like it's a skill to learn to go like, here's your thing, you're happy, go. And it's done. But like software is kind of never done. It's like, it's kind of nice in that way because it's like it outlives your life at the company. Even if you do it right, that'll be running for years after you're gone. So it's more about incremental improvement. Sometimes, big dislocations and you come up with something really new that changes how you do everything. But it's kind of nice. It's never done. You're trying to make a thing that will always make better and better results. So. Yeah.
I assume when you write to book, no Julia.
No, Julia, no.
So how does Julia integrate now?
I'm terrible. I like working in Julia, but it's productive. So I guess that comes from Fugro. The problem we had there is like, got these really strong maths people you want to hire, but they can't necessarily do the production level code. That was always a huge problem there. So you go like, cool, we make something in like Python and it's really slow, particularly on points. You want it to be super fast because there's so many other things. Hyperspectral data is the same, where it's like huge data sets. So each one of these images is a gigabyte. Like it's how big they are when we take them. So, you need really reliable, efficient code. And it's like kind of not really what you can do in something like Python, unless there's a library that just does it for you. So I did it by stealth where I was just naughty and I just wrote some stuff when I actually started and then I got COVID almost straight away. And in the time I was in COVID, I rewrote some of this stuff and I'm like, hey, I did this thing. It's better than your stuff. And then we kind of ran with it. So yeah, so that's a way of getting it introduced. It's pretty normal these days to work in, I'm going to get this wrong, heterogeneous environments, I want to say. So you're going to use lots of different languages for lots of different things. It's becoming increasingly normal. So for hardware stuff, it's like it's all C++ pretty much. Like that's what you do. As soon as you get out from that, you're doing analytics, stuff on top of the data. It's like some bits will be in Python, some bits will be in JavaScript, some bits will be in whatever. That's kind of normal these days. So that's actually a normal thing. So it's getting better. If you go to a big company, like maybe some of the other, when you get some of the industry people who've at more established companies, they might have a more of a enterprise mindset where it's like, you do it in this language this way, and that's the only way to do it. If you're going to newer companies, they'll be more like, oh, we have all this different stuff in all these different languages and you kind of have to deal with it. So it's not, again, I'd say this for this course is like, you're learning Julia, but you're also learning all these other ones because everything's kind of the same in a way. It's just a bit of syntactic difference in how you structure programs. So shouldn't be scared of learning a new language. It's like, it's a good thing to do. I regularly still try and learn a new language every couple of years just to stop getting stale. So that's a good thing to do. Cool. No? Oh, yeah.
What's your least favorite language then?
I don't. I'm sick. Like, I like bad languages. Doesn't sound good. After I said that, she's okay. No, I like whatever's. There's sort of cultures in programming, and you're going to get people who are tools oriented, who really like everything neat and tight. I'm kind of results oriented. So like, there's something fun about doing something in the wrong language badly. I kind of enjoy it. Like, what can you do? It's like MacGyver, what can you make from what's lying around? It's kind of cool. not so good in a company where you've got to support it over a long time, but I kind of don't mind doing things. Yeah. It's fun. It's all fun for me. All right. Oh, well, I'll call it there. Thank you for your time. Thank you for coming. Please eat all the chocolate. It's been really a pleasure.
So just want to thank Paul. This is the third year now.
Yeah.
Third year, third batch. Probably the 300 student is in this batch. Thanks a lot for the.
No worries. Thanks, Yanni.
Taking your time and let's thank Paul.
Well, thank you all for coming.
Andy, his good friend, is tomorrow. Tomorrow, yeah, tomorrow at 6.
Tomorrow, yeah. All right. Thank you very much.
So, yeah, this one is a little more. Yes.
Yeah. Like 1 to 3, I think we can do that. I just